Okay.
Good afternoon, everyone. I welcome the viewers to the 65th Vyakhyaan in PRL ka Amrut Vyakhyaan series of online lectures or Vyakhyans. This series of 75 Vyakhyans began on 4th of August last year and is being organized every Wednesday to celebrate the Platinum Jubilee of Foundation of PRL. The Vyakhyans in this series are delivered by eminent speakers from India and abroad, from diverse fields of science, engineering, management, and arts, etc. We are honored to have the Nobel Laureate, Professor Anthony Leggett, to deliver today's Amrut Vyakhyaan, who is presently based at the University of Illinois. On behalf of the Director PRL, my colleagues, and also on behalf of the Amrut Vyakhyaan Committee of PRL, I extend a very warm welcome to Professor Leggett. Thank you, Professor Leggett, for accepting our invitation and for gracing our celebrations of PRL at 75. We are looking forward to your lecture on the interesting topic, that is, what can we do with a quantum liquid? I would now like to request Professor Navinder Singh to formally introduce the speaker to the audience and to request him to deliver the 65th PRL ka Amrut Vyakhyaan. Professor Navinder, please.
Thank you, Professor Nandita. It's a great honor for me to introduce one of the greatest pioneers of low temperature and condensed matter physics, Professor Anthony J. Leggett. Professor Leggett does not need any introduction for most of this audience, but still for newcomers and students, I will briefly introduce him. Professor Leggett has shaped the theoretical understanding of normal and superfluid helium liquids and strongly coupled superfluids, and his pioneering work on the superfluidity was recognized by a 2003 Nobel Prize in Physics. He set directions for research in quantum physics of macroscopic dissipative quantum systems and the use of condensed matter systems like Josephson devices to test the foundations of quantum mechanics. The very famous Caldera-Leggett model and the famous Leggett-Garg inequality are some examples. His research focuses on superfluidity in highly degenerate atomic gases, low temperature properties of the amorphous solids, conceptual issues in the foundation of quantum mechanics, topological quantum computation, and on cuprate superconductivity, the relative phase fluctuations and the associated Leggett mode in multiband superconductors has been experimentally detected. He has tested the long wavelength, mid-infrared frequency part of the Coulomb interaction in the pairing mechanism of high TC cuprates. One of his book, Quantum Liquids, Bose Condensation and Cooper Pairing in Condensed Matter Systems, Oxford University Press, 2006, is a masterpiece on the subject, in which a very detailed account of the BCS theory and a very rigorous treatment of the electron-electron screening is presented. I have myself used this book to give a course here in PRL, and I would say that it is a must-read for serious students of condensed matter physics. Currently, Professor Leggett is the John D. Catherine T. MacArthur Professor and Center for Advanced Study Professor of Physics at the University of Illinois. Professor Leggett is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, the Russian Academy of Sciences, foreign member, and the Indian National Science Academy. He is a fellow of the Royal Society, FRS, since 1980, the American Physical Society, the American Institute of Physics, and Life Fellow of the Institute of Physics. He was awarded 2003 Nobel Prize in Physics, along with Vetle Ginsburg and Abrikosov for pioneering contributions to the theory of superconductors and superfluids. He was also awarded the Maxwell Medal and Prize 1975, the Dirac Medal 1992, and the Wolf Prize in Physics 2002. He is an honorary fellow of the Institute of Physics UK. He was knighted by Queen Elizabeth II in 2004 for services to physics. With this brief introduction, I request Professor Leggett to proceed with today's Amrut Vyakhyaan.
Thank you very much, Professor Singh, for that kind introduction. It's a pleasure to be able to address this audience at the PRL. My topic today is quantum liquids, or what can we do with a quantum liquid? Can we have the first slide, please? And okay, can we? Yep. Okay, good. Yes, what can we do with a quantum liquid? And the first question, I guess, is what is a quantum liquid? What are the ingredients we need to make one? So next slide, please. Next slide, please.
Sorry.
Okay,
Yeah.
so good. So to make a quantum liquid, we basically need three ingredients. We need low temperatures in order to get a high degree of order. We need quantum mechanics in order to get particles to show wave-like behavior. And we need the system, very importantly, we need the system to be liquid so that the particles can change places. And if we've got all these ingredients, then we may have a quantum liquid. And a quantum liquid is a system which shows not just the effects of quantum mechanics, but in addition, the characteristic effects which follow from the indistinguishability of elementary particles. And I will be interested in these effects of indistinguishability, and in particular, in the special class of quantum liquids, which are superfluids, that is, quantum liquids showing macroscopic quantum behavior. I will, in fact, discuss superconductors, superfluids, superfluid helium, and superfluid helium-4, and also superfluid helium-3 as examples of this. So let me just try to elaborate a little on the various ingredients that we need to make a quantum liquid. Next slide, please. Next slide, please.
I don't know why it's not changing it.
Okay, good. Okay, well, as I said, we need low temperatures in order to get a high degree of order. There are some very familiar examples of that, which I'll show in this slide. If we have a set of atoms or molecules, then typically at high temperatures, they might be liquid, very disordered. The atoms or molecules just moving around at random. If we go to low enough temperatures, they will form a solid where the atoms form a regular crystalline lattice. A second example, magnetism. If we think of the spins of atoms in a solid as like little magnets, then at high temperatures, they may be paramagnetic, oriented pretty much at random. At low temperatures, they'll be ferromagnetic, or they may be ferromagnetic, all aligned together. And finally, a third example is an alloy, say copper and zinc. At high temperatures, you see that the red dots, the copper, say, are distributed randomly with respect to the blue dots. A red dot may be next to a red dot, it may be next to a blue dot. It's a random process at high temperatures. So we have a disordered alloy. At low temperatures, the system orders in such a way every red is next to 4 blues and vice versa. And we have an ordered alloy. So that's the effect of low temperatures. Next slide, please. Next slide, please.
I don't know why it's taking time.
Okay. The second ingredient, remember, that we needed was particles, or it needed quantum mechanics. We needed that particles should behave as waves. And you are all familiar with some examples of this, I think. We have a source of electrons, and we collimate and monochromate them properly. We can shine them through a two-slit device, so-called young slits with electrons, and get them to arrive on a photographic plate where we will see dark and light, a pattern of dark and light lines, just as we would for light. So under appropriate conditions, particles, electrons, which we thought of as particles, are behaving similarly to light, which we've always thought of as a wave. There's a quantitative relation between the particle and wave aspects, the so-called de Broglie relation. That relates a wave-like property, the wavelength lambda, to two particle-like properties, namely the mass and velocity. And the quantity which relates them so as to get the dimensions right is Planck's constant, which is a few times 10 to the minus 34 joule seconds. So very, very tiny on an everyday scope. Nevertheless, under appropriate conditions, we can see particles behaving like waves, but only under certain conditions. Next slide, please. Yep. So the question is when when do we see a particle genuinely behaving like a wave rather than like a particle? In other words, despite the fact that we believe that all particles are described as waves, we don't always see them behaving that way. And that's because very often waves do behave just like particles. If we have a wave with wavelength lambda and is coming up to a slit, say, with a size A, and if the wavelength is very small compared to the size of the slit, then the wave will just go straight on through the slit, pretty much like an ordinary particle. So we won't really be able to tell the difference. To see the difference, see that the particles really are behaving like waves, we need that the wavelength be at least as large as the slit through which we have to pass. So lambda has to be greater than or equal to A. And under those conditions, we get the phenomena of diffraction and interference. The wave doesn't go straight through, it gets spread out in a complicated way. A simple example of that, although it's not the whole story, is the fact that we can, crudely speaking, we can hear around a door, but we can't see around it. And that's because both sound and light are indeed waves. But in the case of light, the wavelength is very small compared to the size of the door, so it just goes straight through. In the case of sound, the wavelength can be quite comparable to the size of the door, so it can be show diffraction and interference. Although, as I say, it's not quite the whole story. So let's just go into the conditions to see wave-like behavior a little more detail. We already saw that we have the de Broglie relation, that lambda is h over mv, and to see wave-like behavior, we need lambda at least equal to I. So to get that, we need that v, the velocity, is smaller than h over ma. On the other hand, the kinetic energy, which is a half mv squared, is Boltzmann's constant times the temperature. And Boltzmann's constant, again, very tiny on the everyday scale, 10 to the minus 23 joules per degree, roughly. So putting those considerations together, we find that the temperature should be less than or equal to h squared over 2m times Boltzmann's constant times a squared, where a is the slit or aperture through which we have to pass the particles in question. Now, that's not really terribly well defined, but in a gas or liquid or solid, it seems sensible to take the width of the slit as something like the spacing between particles, because after all, each particle does have to squeeze between other particles. So putting all those together, we find that electrons can show wave-like behavior for all temperatures in the liquid or solid phase. They may show wave-like behavior. On the other hand, for atoms, the condition is much stricter. We need that the temperature is less than about 20 degrees Kelvin divided by the atomic number. Okay, however, we still have to fulfill a third condition. Next slide, please. Yeah. So we still have to have a liquid. Why? Well, the reason is that usually if we're talking about a gas, then it's very dilute, and so the wavelength is much less than the distance between particles. We don't really see any strong wave or quantum effects. That's not nowadays entirely true. We do have the so-called ultra-cold alkali gas atoms, which can show quantum effects in the gas phase, but that's a relatively new development. So gases won't really fulfill all our conditions. What about solids? Well, we can certainly take them to low temperatures. We can reach the condition that the wavelength is larger than or comparable to the distance between particles. Because in solids, the atoms are packed closely. However, in a solid, the atoms don't change places. And we need the atoms to change places for reasons I'll show you in a moment. And that's why we need a liquid at low temperatures. We need a system such that the wavelength is larger than the interatomic spacing and the atoms change places. In other words, for electrons, that's no great problem because all metals, whether they're liquid or solid, are liquid in the sense we need. The electrons in metals, they can change places easily. For atoms, again, conditions much stricter. We need temperature less than 20 K over the atomic number and also liquid. And in practice, that means either the ultra-cold atomic gases or a much older system, liquid helium, either isotope, helium-4 or helium-3. So those are the, crudely speaking, systems which form quantum liquids. But why? Why do we need the atoms to be able to change places? Next slide, please. Well, because remember, the quantum liquid is defined not just as showing the effects of quantum mechanics, but also of the characteristic indistinguishability of elementary particles. So let's say a word about that. Because elementary particles behave like waves, it's impossible to tag them or put a code on each of them. Imagine that we start with a couple of, say, electrons, and we try to call one of them Bob and one Fred. Well, unfortunately, they then move through one another, move around and past and through one another, behaving like waves. And so at the end of the day, you can't really tell which is Bob and which is Fred. If we find one of them down at the bottom left and the other at bottom right, they could have moved according to the middle diagram, or they could have moved according to the the diagram at the bottom. We don't know the difference. We can't know the difference. But in order for that property to be important, the particles in question must be able to change places. That's exhibited very nicely by the rotational and vibrational properties of the carbon molecule. If I have a carbon molecule, which remember is C2, just 2 carbon atoms, if it's made out of 2 different isotopes of carbon, say carbon 12 and carbon 13, then really there are no effects of indistinguishability. But if it's made of 2 carbon 12s, then they are indistinguishable, and you may be able to get some effects of it. And what is very interesting is that you do get effects. Well, let me start the other way around. You don't get any effects on the vibrational levels, and that's because in vibrational levels, the atoms are simply oscillating like this, they're not changing places. However, in the rotational levels, they're rotating around one another. They are changing places. And so you do see the effects of indistinguishability. And that is actually seen in the spectrum of the carbon molecule. Okay, now, next slide, please. Okay, one very spectacular effect of indistinguishability is so-called quantum statistics. And this is very different, it turns out, for the 2 different classes of particles, many of you know this, which depend on the spin of the intrinsic angular motion of the particle in particular units. H bar, that's Planck's constant over 2 pi. If the spin of the particle in these units is half integral, a half or 3 halves or 5 halves, then there are fermions, they're called fermions, and they then are very xenophobic. They tolerate at most 1 particle per state. And so they fill up the states of lowest energy up to a characteristic energy called the Fermi energy. And after that, the distribution basically drops sharply to 0. So that is not in itself terribly interesting. Much more interesting is a class of particles called bosons, which have, in the appropriate units, they have spin 0 or H bar or 2H bar, whatever. And bosons are very gregarious. They love to have a lot of particles in a single state. And they love it so much that at low temperatures, low enough temperatures and high enough densities, you may find that you pile up a non-zero fraction of all the particles into a single 1 particle state. Generally speaking, the lowest energy state, but it need not necessarily be so. Next slide, please. Why does that happen? I have here a rather intuitive argument and a quantitative one. I think we can probably skip the quantitative one, but let's just go through briefly through the qualitative intuitive one. Suppose that we have to distribute n objects between 2 boxes. What's the probability, P of m, of finding m of those objects in 1 box? Well, suppose that we're talking about ordinary objects like, I don't know, oranges or billiard balls or something like that. So they're distinguishable in any ordinary sense. Then it turns out the problem is just the same as tossing an unbiased coin. And you find that the number of ways of getting m particles in 1 box is very strongly peaked around a half. So if you toss 100 coins, then the odds are that you're going to get somewhere near 50 heads and 50 tails. You won't get exactly that, but you'll probably get something close to it. That's not what I want to emphasize. What I want to emphasize is that for these ordinary distinguishable objects, like coins being tossed or like oranges being distributed, the probability of getting the extreme results, that is, all heads or all tails, is very small, very tiny indeed. And that's given formally by the so-called factorial formula, binomial formula. Now, that means the result of that is that if I now try to bias the possibility of getting a lot of particles in one box rather than the other, say by making the energy of that box lower than the other, it really has rather little effect. It'll shift the distribution a little, but it really won't do a lot to it. But now suppose that our objects are indistinguishable, as they would be if they were bosons. Then the number of ways of distributing the object so that we get m in one box is independent of m. You can easily convince yourself of that. So that in turn means if I now bias the distribution by making it more favorable in energy to put things in one box, then I'm quite liable to end up with all of them in a single box. And that's basically the phenomenon of Bose-Einstein condensation, or BEC. As I say, there is a quantitative argument, and some of you might recognize it from textbooks, but I think we can probably afford to skip that. It gives roughly the same result. But it also gives the additional information that this phenomenon of Bose condensation really tends to happen when the temperature is lower than this characteristic value, which you might recall is what we got earlier by a rather hand-waving argument. So the result is essentially the same. Anyway, what is special about Bose condensation? Next slide, please. What is special, I think, is rather well illustrated by this figure from this picture from the cover of Science in 1996. That was when Bose condensation in the ultra-cold alkali gases was first realized. Science, at the end of the year, Science always declares a molecule of the year, and in 1996 it declared the molecule of the year to be the Bose condensate. And so it has a picture of the Bose condensate as a platoon of well-drilled soldiers, all marching exactly in step, all doing exactly the same thing at the same time. And then you see it also has these other guys who are different colors and all doing their own thing, and they are the fraction of the atoms which are not Bose condensed. But let's focus on the Bose condensate here. So they're all doing exactly the same thing at the same time. And that's true whether or not they're in the equilibrium state or in a highly non-equilibrium state. That's a rather special thing about the Bose condensate. It doesn't really matter. Okay, so now let's try to see, having defined what we mean by Bose condensation, let's try to see some examples of that. Next slide, please. Yeah, the first example is superconductivity. And well, technically, superconductivity is defined as the flow of current when there is zero voltage applied across the sample. When I often do demonstrations of superconductivity at the farmers market in my hometown, Champaign-Urbana, in front of school kids. And the way I do it is usually this. I usually start with an ordinary copper tube, hollow copper tube. And I first of all show the kids there's nothing special about the tube by just dropping a little pebble down. The pebble just goes straight through, no problem. I then take a little magnet and show them that it is magnetic and try to drop it down the tube. And if you've done this experiment, you'll know that it does drop down the tube, but it does so much more slowly than the pebble. It'll take a few seconds to go down the tube. Why is that? Well, it's because as the magnet moves downwards, it creates an electric field. The electric field will then generate a current around the tube, and that current in turn will generate a magnetic field which tends to hold the little magnet up. But eventually, of course, although we generate the current, it will die away. And when it dies away, the magnet can fall further. And so eventually it does, after a few seconds, come out at the bottom of the tube. And then I asked these kids to imagine what will happen if the current does not die away, but keeps on flowing forever. And some of them guessed correctly that what will happen is that the magnet will just stay suspended for it. And then I show them that if I have a pellet of high temperature superconductor, say yttrium, barium, copper oxide, take the pellet, cool it in liquid nitrogen, and then take the magnet and try to lower it. Sure enough, it doesn't fall. It stays suspended in the air above the pellet. And so that is the phenomenon which you know as superconductivity. Now, for most, until quite recently, superconductivity occurred at relatively low temperatures. This is as in the case of aluminum, shown in this figure here. Next slide, please. But here is a graph of the highest temperature at which superconductivity has been achieved over the last 100 years or so. And you will see the enormous leap in 1986, when we got to about nearly half of room temperature. And then if you look at the top right of the figure there, you'll see that this dot marked 2014. And that was the year in which superconductivity was achieved, not quite at room temperature, but very close to room temperature. Unfortunately, this was not done in ordinary laboratory circumstances. It was done under enormous pressures, several billion atmospheres. So right now we do have pretty much room temperature superconductivity, but only under these enormous pressures. And people are trying very hard to figure out how you might realize superconductivity at room temperature, but at ordinary atmospheric pressure. So far they haven't got there, but the hope is they might. Anyway, let's try to think a bit about why this phenomenon is related to Bose condensation. Why is it that if I start a current, it will continue in a superconductor, it will continue to flow forever? Next slide, please. Well, we already reviewed the fact that in order to form a Bose condensate, particles have to be bosons. The electrons in metals are not bosons, they're fermions. So they do, at first sight, they behave in the very xenophobic way. They just form a so-called Fermi sea, and that's not particularly interesting. However, a compound object, which consists of an even number of fermions, has an integral spin, 0, 1, or 2, or so forth. So, and so that can form a boson. One example of that, which we'll see later, or we'll talk about later, is the helium-4 atom. That consists of 2 protons, 2 neutrons, 2 electrons. So even number, it basically forms a boson and can undergo Bose condensation, and we'll talk about that later. But let's just stick with electrons for the moment. Next slide, please. So if I take pairs of electrons and put them together, then they can form sort of dielectronic molecules, and they can automatically undergo Bose-condensation. Now, you might think that the electrons in a superconductor are forming these dielectronic molecules like in the top left of this slide, tightly bound dielectronic molecules. That may be the case. Some people think that is the case in the new high temperature keep rate superconductors. But for the old-fashioned superconductors like, say, aluminum or lead, that does not appear to be the case. They're doing something a bit different. They're behaving as in the top right of this slide. You see that you have these two marked electrons, which are far apart, but they're nevertheless strongly correlated. That is, they don't move independently. They, in some sense, move together, despite the fact that there are many, many other electrons between them, all forming their own pairs. People sometimes compare this to a form of modern dance in which my motion may be correlated with that of my partner, but she is way across the room, and between us there are any number of other pairs, any other couples forming their own pairs and correlations. Now, one very interesting point, at least in the simplest theory of superconductivity, the so-called PCS theory, this is due to my colleagues at the University of Illinois, Bardeen, Cooper, and Schrieffer, way back in the 50s of the last century. In this theory, once the Cooper pairs are formed, they must automatically undergo Bose-condensation. And that means, you remember, they must all do exactly the same thing at the same time. Also in a non-equilibrium situation, not just in equilibrium. So let's try to imagine how this gives us some intuition about how superconductivity occurs. And let's make an analogy here. Let's imagine a forest. It has to be a natural forest, not a plantation. So the trees are distributed at random. And imagine that we take a group of school kids and we instruct them simply to run into the forest. And we give them no special instructions beyond that. Well, the kids will start off running together in the same direction into the forest. But after a time, one of the kids will run up against a tree. And having no special instructions, she will swerve to avoid it. And again, not being instructed otherwise, she'll go on running in the new direction. And the same will happen with the other kids. And you see that after a rather short time, the kids will all be running in random directions. And that's basically the analogy of what happens to the electrons in a normal metal like copper at room temperature. You give the electrons a kick, for example, by dropping the magnet, so causing an electric field around the tube. They will initially all move off together, but after a bit, one electron will run into an impurity, be scattered by it, and go off in the new direction. And after a short time, the electrons will all be running in random directions. There will be no current anymore. So in other words, the current will die away, typically in about a billionth of a second, very fast indeed. And that is the so the electrons in a normal metal then are the analog of school kids in the forest. But now let's imagine that we have the same forest, but we don't have a group of school kids. We have a well-drilled military platoon. The soldiers are instructed that as best they can, they must always keep in step. If they get out of step, they must drop back into it as soon as possible. So again, the soldiers go off marching into the forest. After a bit, one soldier will run up against a tree, and he will swerve to avoid it. But he has instructions. to get back in step with his comrades the moment he can. And so he will get back into step with the rest of them. The same will happen to all the other soldiers. And so even after a long time, all the soldiers will still be marching in the same direction. And that's the analog of what happens to the Cooper pairs in a superconductor. Even if one Cooper pair, or perhaps one electron of a Cooper pair, runs into impurity, well, it'll sort of avoid it, but then it'll drop back into step with all its fellows and go on, as it were, marching. And so even after a long, long time, the current will still continue to flow. So I think that's reasonably straightforward to visualize. But there was something actually a little more about a superconductor. As I said, initially the experiment I do is to take the pellet of high temperature superconductor, yttrium barium copper oxide, cool it in liquid nitrogen so that it becomes superconducting, and then take the magnet with a pair of tweezers and try to lower it onto the superconductor. And as we said, it doesn't do it, it floats. And I've done this experiment many times. But there's something a bit more subtle. Suppose I try to do the experiment the other way around. Suppose I first take my tweezers, take the magnet, the YBCO, the pellet, is just sitting there at room temperature, no liquid nitrogen at the moment. So I take the magnet with my tweezers and I just put it on top of the superconducting, the YBCO pellet. Nothing happens, it just lies there, right? I mean, the pellet is in the normal phase, so nothing special, right? But now I pour the nitrogen on the pellet. And then, lo and behold, as soon as the metal becomes superconducting, the metal spontaneously lifts up and floats. That's a slightly more delicate experiment. It takes a little more, you have to get things a little more right to get that to work, but it does work if you get it right, okay? That can't be explained by infinite conductivity because you haven't done anything. All you've done is to cool the metal, and lo and behold, the magnet is levitated off. Okay, well, it's a little complicated to see how that works for a superconductor, but there's something very parallel, which happens for superfluid helium-4, and so theoretically, these liquid helium-4 is very similar to a superconductor. So let me talk about that explicitly. So next slide, please. Yeah. Okay, so imagine, here's the experiment. Suppose we take a circular flower bowl, say, and so-called annular container, and we fill it with liquid helium-4. We rotate the container very, very slowly. Typically, to make this work with an ordinary sized container, it would need to be about 1 revolution per hour. Well, at high temperatures, the helium just behaves like water. What would water do? Well, initially maybe it would be at rest, but after a bit, after you've been rotating for a bit, the water will come into equilibrium with the rotating container. You can do this experiment if you want to with an ordinary glass of water on an old-fashioned gramophone turntable. It's essentially the same as this. Okay, so once the glass is fully rotating, then after a few seconds, the water will be rotating with it. Nothing mysterious at all. However, if I now cool the helium through the so-called superfluid transition, which is at about 2 degrees absolute, then I find that it comes out of equilibrium with the rotating container and ceases to rotate, apparently in the frame of the laboratory. Actually, it's probably not. We think it's probably at rest in the frame of fixed stars, but it's a little difficult to prove that quite rigorously. Everything everything is consistent with the assumption that it's at rest in the frame of fixed stars. Why? Why does this work? Well, there's a general principle that the average angular velocity of the atoms, let's call that omega bar, should be as close as possible to the angular velocity of the container. Fine, but wait a minute. The single atom states must obey the so-called quantization condition, which some of you may be familiar with. That says that an integer number of de Broglie wavelengths of the wave describing the atom must be equal to the circumference of the ring. So n lambda is 2 pi r. Now the de Broglie wavelength lambda is h over nv. Put those together, and what you find is that the angular momentum L, mvr, must be quantized in units of h bar, that's h over 2 pi. That many of you will be familiar with that result. So that in turn means that the angular velocity, which is the angular momentum divided by the moment of inertia, that is just n times the omega sub c, which I defined higher up. So, well, how come then that water or helium at high temperatures rotates with the container? Well, the answer is that for a normal non-Bose condensed system, there are many different single particle states occupied. A typical value of n in that formula omega is n omega c is something like 10 to the 7th under ordinary conditions. So in order to get omega bar equal to omega, all you have to do is just to shift the atoms slightly around between the states. And sure enough, you'll find that the water or the helium at high temperatures is indeed rotating with the container. But now let's go to low temperatures below the transition temperature for Bose condensation. Then you find that almost all the atoms are in the condensate, and that means they must all have, remember, the same, they must be behaving in the same way, they must have the same value of n. So if that value of n is n sub 0, that means that the angular velocity of the liquid cannot be just anything. It has to be n0 times this omega sub c. That's the quantity defined at the top of the slide there, h bar over mr squared. And so if I start from rest and rotate the container and gradually increase the speed of rotation, I find that as long as I'm below a half of omega c, then as you see in the bottom right of this slide, nothing happens. The liquid just stays at rest, stays with n0 equals 0. Once I get past half of omega c, then I jump up to a value n0 equals 1. The liquid is now actually rotating faster than the container. Sticks there until I get to 3 halves, jumps again, etc. And this is, although the experiment is, of course, as usual, more complicated than this simple picture, this is essentially verified in experiment. So again, you see the effect of a Bose condensation, the fact that all atoms must be doing exactly the same thing at the same time. The final example I'm going to discuss, and I probably won't have time to discuss this in much detail, is something which is very dear to my own heart, which is nuclear magnetic resonance in superfluid helium-3. Last slide, please. Okay. Suppose that I take a nuclear spin in so a small nuclear magnet in a magnetic field, or say H. If I tip the spin away from the field, then it will precess around it. And the rate of precession is given by the formula, nu, frequency, is gamma H. Gamma is a quantity called the gyromagnetic ratio, and H is the magnetic field. Now, in helium-3, gamma is well known. Its well-known quantity is 3 kilohertz per Gauss, roughly. But anyway, the rate of precession will measure the magnetic field. But how do you measure the rate of precession? Well, what you do is to apply an oscillating field transverse to the external field, and the field will be strongly absorbed when its frequency is equal to the precession frequency. So in that way, one can measure the magnetic field, or apparently one can. And these experiments have been done for many, many years in liquid helium-3, and above a temperature of about 3 milledegrees absolute, that is something like a 100,000th of room temperature, everything behaves just as expected. The precession frequency, nu, is just equal to gamma times the external field. So that's the so-called Larmor frequency. Okay, very standard, very textbook, nothing at all mysterious. However, in 1972, the group at Cornell University in the United States carried out measurements, nuclear magnetic resonance measurements in the standard geometry, lower temperatures than this. And what they found was something very surprising. They found by other measurements that there were 2 new phases of helium-3 below about 3 milli K, so-called A phase and the B phase. And they found that when you went into the A phase, the nuclear magnetic resonance frequency started shifting up above the Larmor frequency. And then when you got to the B phase, and then when you made the transition into the B phase, the NMR frequency simply dropped back to the same value as in the normal phase. So, very remarkably, what they found was that the shift in the A phase was not simply proportional to the external field. There was a so-called Pythagorean formula, as noted at the bottom of this slide in red. That was a real mystery. Next slide, please. Next slide, please. Yeah. We're just repeating. That's just repeating what was at the bottom of the last slide. So what is the simplest interpretation of this formula? Well, the simplest interpretation is that you have the ordinary external field due to your whatever magnet you're using. So I'm not going to get this right because I can't see myself properly. But anyway, there is generated an extra field transverse to this external field. So the total field is now given by the Pythagorean expression, and the nuclear spin then just precesses around that, not around the external field. So that will be a very sort of ordinary and actually not particularly interesting explanation of what was going on. However, it's a problem. Where does this extra internal field, the transverse one, come from? The only possible origin is the other nuclear spins. Remember that you're talking about helium, so the electrons are just about totally inert. So the only other source of the internal field is the other nuclear spins. And even when 2 atoms are packed as tightly as they can be against one another, the maximum value of the field of one nuclear spin on another is less than a Gauss, whereas the experimental value, which you need to explain the shift of the resonance frequency, that is this H internal, is something like 30 Gauss. And when I realized this, my first reaction was that this is so weird and so extraordinary that it might be the first evidence for the breakdown of quantum mechanics under these very extreme conditions. Very low temperatures, a very dense system with obeying really in fact, the coldest quantum liquid that we'd ever managed to get. Was something going wrong with quantum mechanics. So initially I set out to show that if quantum mechanics was right and if statistical mechanics was right, these results couldn't occur. Well, of course that didn't happen, or you'd heard about it. So next slide, please. Well, we could do a more sophisticated approach, which is what I tried to do way back in 1973. And it turns out, first of all, that the simple classical argument with a simple transverse field related to the external one is a bit too naive. Nevertheless, you do indeed predict a formula of the Pythagorean form where H0 is squared is proportional to the average value of the nuclear dipole interaction energy. So let's just think for a moment about that. The nuclear dipole, two small nuclei interact like two little magnets, just like two magnets in the laboratory. If you take two magnets in the lab and they're parallel, they're magnetized parallel, you try to put them side by side, they don't like it. They much prefer to go into the good orientation, the one on the right, where they're end to end. But the energy difference between the good and bad orientations in the case of the helium-3 nuclei is something like 10 to the minus 7 degrees Kelvin per pair. The thermal energy at the temperatures you're talking about is 10 to the minus 3 kelvins. So at first sight, the thermal energy should totally overwhelm preference for end-to-end over side to side. And so you'd only get a tendency of the order of 10 to the minus 4. And what that will mean in turn is that the experimental value of the dipole energy, which you need to fit the characteristic field, is much too small. What you need is a preference for good over bad, which is not of order delta E over the thermal energy, but of order 1. How on earth could you get that? Next slide, please. I lay awake for 3 weeks, I think, at night, trying to see how this could be. And finally, I did come up with a solution, and although I'm getting quite close to my time, let me just briefly try to explain what the solution is. The easy way to understand it is by comparison with an ordinary ferromagnet, like say iron. In a ferromagnet, you have individual atomic spins or magnets. They're in an external field, and they would rather lie along the field than against it. But the difference in energy is rather small. It's delta E here. Above the Curie temperature, at high temperatures, and paramagnetic phase, the spins behave independently. So the thermal energy competes with delta E, and the polarization is only that ratio, delta E over E thermal, very small compared to 1. Below TC, in the ferromagnetic phase, there are strong exchange forces, absolutely nothing to do with the ordinary Zeeman energy in the external field, quite different nature. These are these strong exchange forces, they constrain all the spins to lie parallel. Now you have to choose. Do you have all your spins along the field or all against them? All good or all bad? Now the energies which are competing with the thermal energy are not delta E, but rather n times delta E, which is huge because n is 10 to the 23 or whatever. So that means the polarization is indeed of order 1, and that's what I've seen experimentally. So what's the analog in helium-3? In liquid helium-3, the difference in energy for the good orientation over the bad one, only about 10 to the minus 7 K. In the normal phase, high temperatures, the pairs behave independently. So the thermal energy is competing with delta E. The polarization, that is the preference for a good orientation over a bad one, is only of the order of delta E over E thermal, and very small compared to 1. let's assume that in the A phase, somehow the strong van der Waals forces constrain all the pairs to behave in the same way. In that case, all the pairs must either behave in the good way or in the bad way. Just as in the case of Ireland, the preference for good is over bad is now not delta E, but n times delta E, where n is huge, 10 to the minus 23. The polarization can be of order 1, and we can explain the experimental data. Why should they all behave in the same way? Why should all the pairs behave in the same way? The obvious explanation is that for the same reason as the Cooper pairs in a superconductor. In other words, they're forming pairs. They're forming a sort of Bose-Cousins state of pairs, and that, crudely speaking, is what we now believe to be the case in helium-3. Well, I do have one more slide, but I think perhaps since I think I've probably overrun my time already, I should perhaps stop. And if people do want to hear about some of the other dramatic things which may happen as a result of this phenomenon of effective Bose-condensation in liquid helium-3, perhaps I can ask a question. Okay. Thank you.
Yeah, thank you, Professor Leggett. Thank you very much. So the next conference session will be taken by Namita Mahajan.
Thank you, Professor Leggett, for a very, very clear and lucid talk, which was laced with simple examples, and yet you were able to point out the subtleties and ending upon touching some of the aspects of superconductivity and superfluidity, which itself is a very vast subject. So it's very difficult to cover everything in a short time. Now, as everybody would have realized, this is what happens when we hear about something from the master directly. So now the floor is open for the questions. Professor Leggett, we hope you have some time for taking up some of the questions. So I request the viewers on the WebEx panel to raise their hands and they can unmute themselves one by one. I'll keep calling their names, and my friend will post other questions from the YouTube channel onto the WebEx chat box, and I'll read them for. Yes, Namita. Yes, please go ahead. Please go ahead.
Yeah. So my question is related with this NMR. So in a BCS superconductor, so we have this Hebel-Schleicher peak below TC, and on the other hand, I mean, there is a rise in the relaxation rate, NMR relaxation rate, and on the other hand, if we look at the ultrasound attenuation shows a decrease. So that is understood due to the coherence factors, the BCS coherence factors.
Yes.
Do we have a similar analogous phenomena in helium-3, Hebel-Schleicher kind of phenomena?
Interesting question. There really is no direct analog of that in helium-3 because in an ordinary superconductor, the main reason why the nuclear spins are relaxing is because of interaction with the electrons. And that's why the Hebel-Schleicher peak does indicate, is a very important clue as to what is going on in the electron system. Although it's the nuclear spins which are doing the relaxing. Now in helium-3, in liquid helium-3, the situation is different because the electrons are very, very inert. I mean, they're just in the 1s state of the helium atom, so they really can't do anything interesting. So although the nuclear spins do in fact relax, the process is very, very difficult and slow. And in fact, under appropriate conditions at low enough temperatures and with appropriate sample walls and so forth, it can be, I guess it can be a order of days for liquid helium-3. So although in fact there are, when you get into the superfluid phase, there are some very interesting phenomena which take place in the nuclear spin relaxation, but they're really entirely associated with the nuclear spins themselves, and really there's no analog to the Hebel-Slichter. I should say the theory of this is actually quite messy. We do have a theory of why the nuclear spin relaxation speeds up, but it really doesn't have much to do with the Hebel-Slichter business.
Thank you, sir. Thank you.
You may raise your hands on the WebEx panel, or you could unmute yourself and directly ask the question. In the meantime, I'll just look at the chat box once. Yes, please go ahead.
Yeah, so I have one question. So different superconducting materials, they have different transition temperature. So what are the parameters that decide this transition temperature or the formation of Cooper pair below that transition temperature?
Okay, well, I think we have a relatively widely believed and plausible answer for the old-fashioned superconductors. That means, crudely speaking, things like tin, aluminum, lead, mostly the superconductors that were known before about 1975 or so, and are believed to be well described by the BCS theory. In that, for those superconductors, the usual belief is that the formation of Cooper pairs and the temperature, the maximum temperature at which this happens, is determined by the competition of the bare Coulomb repulsion between electrons, which never favors pair formation, but that can be overcome by the virtual attraction generated by exchange of virtual phonons, virtual lattice vibrations. And so what determines TC, or indeed what determines whether superconductivity occurs at all in a given metal, is this competition between the Coulomb repulsion and the phonon attraction. One does know enough about the microscopic structure and the nature of the lattice vibrations and so forth, that nowadays one can sometimes make a reasonably good prediction of what the transition temperature of an old-fashioned superconductor is likely to be. And people have got quite good at doing this. For the more recently discovered classes of superconductors, not just the cuprate high-temperature superconductors, but a whole lot of others, like, say, the ferrochniptides and strontium ruthenate and a whole lot of others. We really don't have such a good theoretical understanding. There seems to be a general preference for strongly layered materials. All the cuprate high temperature superconductors are indeed strongly layered. So they have these copper oxide planes, which are very strongly two-dimensional in nature. And the same is also true of some of these other more recent materials, ferrochniptides, strontium ruthenate, one or two others. People have got all sorts of prescriptions for trying to predict transition temperatures, but we really haven't been so good at that. In fact, the transition temperatures of the cuprate range over something like an order of magnitude from something like 10 degrees absolute to about 150 degrees absolute. One thing that does seem to be helpful to a high transition temperature is that you have to dope to get a high transition temperature. You don't just need a cuprate, you need to dope it correctly. That is, you need to have certain kinds of chemical impurities. And there is a characteristic number of impurities or extra electrons which you have to dope in. And one thing which seems to be important is that it's best if these extra electrons which you need to dope it with do not come from atoms which are close to the copper oxide planes. Because if they are close to the copper oxide planes, then the chemical impurities which you need to supply them tend to interfere with what's going on in the planes. They act as extra scatterers and so forth. So generally speaking, you find that the best, that is the highest temperature, cuprate superconductors are ones where the donor atoms, the ones which are giving you the extra electrons, are quite widely separated from the copper oxide planes. And that does seem to be a general rule of thumb. And there are other similar rules of thumb, but as I say, we don't really have it as quantitative a theory as we do for the old-fashioned superconductors.
Okay, thank you.
Yeah.
So in the meantime, Professor Leggett, let me ask a very simple question. I am a particle physicist, so I'm just wondering, cuprate superconductors do show some very non-BCS-like features, like let's say pseudo gap and phase and etc. Also, what we have heard from various talks is that cold, and you also mentioned that cold atomic systems where phase mixing etc. happen also show very strange features in their own right. I was just wondering whether or can the cold atomic systems be manipulated in a way that they also show, or they can show features like pseudo gap, phase, etc. I may be totally off the track, but I was just wondering whether.
No, not at all. In fact, no, this has been a very interesting development over the last, I don't know, 15 years or so, I guess. One theory about the cuprate superconductors is that indeed in certain parts of the phase diagram, the so-called underdoped region of the phase diagram, the electrons really are forming these rather tightly bound almost dielectronic molecules. Now, and that these are then undergoing some kind of post-condensation. Now, in the ultra-cold atomic gases, it turns out you can actually tune the interactions in such a way as to go continuously from a situation where you have these tightly bound sort of real diatomic molecules to a regime in which you have something much more like the Cooper pairs, which are thought to exist in old fashioned, that is, very large objects, large compared to the distance between the atoms. That's the so-called BEC-BCS crossover. That's been a major subject of research in the ultra-cold gases over the last 15 years or so. And generally speaking, you do find that in the BEC, the region where you're close to BEC but not really an extreme limit there, you do get something very like a pseudo gap, which is forming, and the behavior is qualitatively similar to the cuprates.
Thank you very much. Any other questions?
Can
Yes, please, Navidar. Yes, please go ahead, Navidar.
Yeah, Professor Leggett, so this is regarding the pairing mechanism in this liquid helium-3. So in the BCS superconductors, the phonons are mediators of the pairing. So in the case of helium-3, is it the van der Waals forces, or is it the magnetic spin fluctuations, which are the mediators of the force binding the two helium-3 atoms together?
Well, if I understood correctly, I'm probably didn't hear too well. Your question is, in helium-3, is it the van der Waals forces, or rather spin fluctuations, which tend to bind the Cooper pairs?
Yes.
Yeah. Okay. Well, I think actually that is not not a real alternative, because at the end of the day, well, at the end of the day, the forces between two helium atoms, whether they're in free space or in a liquid, has to go back to the Coulomb interaction plus the effects of the Pauli principle. Okay, so so that's what you're really talking about. The van der Waals forces are in some sense a more direct effect of the Coulomb interaction. Spin fluctuations, again, you can regard them as a consequence of the van der Waals forces. So, so I think a more probably a more a meaningful question is: are the ultimate results of the van der Waals forces, which in turn, remember, are a result of Coulomb forces, are they better represented by a spin fluctuation picture, or by, let us say, a picture in which the most important process is exchange of excitons or something else? I think most people would say that in helium-3 there's a lot of evidence that spin fluctuations are an important phenomenological component. But again, it's a quantitative matter, and people spent a lot of energy over the last 50 years trying to work out exactly how important spin fluctuations are relative to, say, transverse current fluctuations or other things.
Yeah, so like in the BCS, there is this isotope effect is the smoking gun signature. So you change the isotope, the transition temperature changes. So is there any handle on the helium-3? I mean,
Well,
to smoking gun signature of the spin fluctuations, are there any?
well, no, I mean,
Not yet.
yeah, you're right. Of course, in the old-fashioned superconductors, the isotope effect is usually taken as a smoking gun for the importance of the electron-photon interaction. Certainly, you couldn't get it out of any theory in which the ions were static. So yeah. No, in helium-3, as I say, since you, in a typical metal, a typical superconducting metal, I think you can ask the question, a sort of yes/no question. That is, can say the experimental dependence of the transition temperature be explained in a picture in which the nuclei are the ions are static? Answer: no for the old-fashioned superconductors, probably yes for the cuprates. So it is a sort of yes/no question. I don't really think there's any similar yes/no question that you can ask in the case of helium-3. All you can ask is, can we put some kind of quantitative weight on how far a phenomenological spin fluctuation theory can account for all the data, and then that becomes a matter of opinion, really, between different groups of theorists. I think most people would say probably quite a bit of it, but probably not 100%.
Thank you.
Any other questions from anybody? I don't see any questions in the chat box. We still have a few minutes. So,
I wonder if we have a few minutes, perhaps I could just show the last slide, which I had to omit.
sure, please.
So I think it is rather amusing, and certainly the particle physicists in the audience might find this quite interesting. So if we could just go to the last slide. Not thank you, but the one before that. Okay, great. Yeah, well, as we saw, I've been emphasizing the fact that in the NMR behavior, the ultra-weak effects are amplified. The ultra-weak effect of the nuclear dipole-dipole interaction, a very tiny interaction, that is amplified enormously by Bose condensation. And so let's ask the question, are there other kinds of effect which might be similarly amplified? And in fact, there's several, and some of them are actually seen experimentally, but the one I think that I've been most fascinated by is one I actually dreamed up way back in the 70s or 80s of the last century. But the effects of the neutral current part of the weak interaction, which violate P but not T. That's, I think, something like 99.5% of the weak interaction. Could you see the effects of that amplified by Bose condensation in superfluid helium-3? Well, for a single elementary particle, if you think about the electric dipole moment it can have, if it has one, it must be, by the Wigner-Eckert theorem, it must be proportional to the total angular momentum, J. And that formula, that D is proportional to J, violates not just P, but also T. So you're not interested in that. Helium-3b, the B phase of helium-3, actually we probably need to go just back one more to illustrate this point. Can you just go back to the one before this one? Could we just go back to the slide before this one? Yeah, great. This is, yeah, in the B phase of helium-3, you have a very peculiar kind of ordering. If the red arrows represent, say, spin, and the green arrows represent orbital, the relative orbital angular momentum of a Cooper pair, then you see that in the normal phase, both the red arrows and the green arrows are disordered, and there's no relation between the red and green arrows. In the B phase of helium-3, not the A, but the B phase of helium-3, you see that the red arrows are completely disordered, the green arrows are completely disordered, but there's always a definite relation between the red and green arrows here. And that means that there is a special quantity, namely L cross S, the vector cross product, which is non-zero, despite the fact that S and L themselves are zero here. Okay, so let's go back now to the slide we were on. That's the next one. So we find we can actually form an electric dipole moment along this characteristic vector L cross S, and that will violate P but not T. Now, if you were to work this out for a single Cooper pair, it's just laughably tiny. However, all the pairs have the same value of L cross S, so it's multiplied by a factor of 10 to the 23 or so. So it could come with an experimental reach. I actually suggested this to a few of my experimental colleagues way back in the 80s, and they looked at it quite hard, but thought they didn't quite have the sensitivity to see it. Well, over the last 40 years, both cryogenics and metrology have improved enormously by many orders of magnitude. And now it seems that there may be a real possibility of actually seeing this effect in experiment. And in fact, there's at least one experimental group which is seriously thinking about looking for this. And I think this would really be very amusing if we could see it. We'd see this, the effect of this tiny, not just the neutral, the weak interaction, which is by itself is, as it were, exotic enough, but the neutral current part of the weak interaction actually showing up at the macroscopic level in the laboratory. I really think if we could see that, that would be very amusing. Okay, thank you. That was what I wanted to say about that.
Thank you, Professor Leggett, for a very interesting talk. Now, since there are no more questions, I'll now invite my colleague, Professor Satyendra Gupta, to give the vote of thanks. Professor Gupta.
Thank you, Dr. Namit. It's my honor and privilege to give a vote of thanks. So on behalf of PRL's Amrut Vyakhyaan committee, I thank the speaker, Professor Leggett, for accepting our invitation and delivering an excellent Vyakhyaan on quantum liquids. We appreciate your time for the discussion during question and answer session. I thank our director, Professor Anil Bharadwaj, our dean, Professor Pallam Raju, and the chairman of Amrut Vyakhyaan committee, Professor Nandita Srivastav, for their support and guidance in hosting and conducting this Vyakhyaan. A sincere thanks to the audience who have joined us on Zoom and on YouTube. Please do visit us, our web page, and also our YouTube channel for update and info about the upcoming Amrut Vyakhyaan. With this, I now propose to end the 2 days Vyakhyaan. Thank you all. Have a nice day and nice evening.